And go.
Hi, my name is Brooke Eshback, and my project is called Efficient Heuristics for the CableTrench Problem and its Variants. So in this presentation, I'm just going to do a brief introduction to the problem, talk about some heuristics and variants, talk a little bit about some coding that's been done for this project, and then where I would like to go from here. So for starters, when we're talking about the CableTrench problem, we're going to think about it as we have a campus with multiple buildings, and we're trying to connect all of them back to a central building, maybe an IT building or something like that. And to do that, we have to dig trenches to lay underground cables in. So when we do that, we're going to want to minimize the cost of the trenches and the cables, digging the trenches and laying the cables, so that we spend as little money as possible on this project. And that's actually one of the many real-world applications of the CableTrench problem. And other ones include things like medical imaging, irrigation, logging, carpooling, and there's a lot of others too. But in mathematics, we're going to look at it as we have a weighted connected graph, and we designate one vertex as the root vertex, and then we have to try and connect all of the other vertices back to that root. And then we have additional parameters for our trench and cable costs along each edge. So we have G as our connected graph, V1 is our root vertex, WE is our positive length or weight for each edge, and then we have tau and gamma are our trench and cable costs respectively. So this is an example of a graph that we would use for the CableTrench problem, and it's actually one that we are going to look at throughout this presentation. And it's relatively small. It only has 9 vertices and 16 edges, and you can see that all the edges are weighted. And as I said earlier, the goal is to minimize both the cost of digging trenches and the cost of laying cables to connect everything back to that root vertex. So we're going to look at some different cases. So for starters, if the cost of cables is free and gamma is equal to 0, then we have what's called a minimum spanning tree problem. And that just means that we're going to choose edges in such a way that we minimize the total sum of edge lengths. So we're minimizing our trench weights since cables are free and we don't care how many of them we have to lay or how long they are. And on the other end of the spectrum, we have the case where trenches are free and tau is equal to 0, and that is what's called the shortest path tree. And there we have, we would choose edges in such a way that the overall distance from each vertex back to that root is minimized. So our total cable weights would be minimized. But obviously in the real world, nothing is really free. So we have to consider cases where both tau and gamma have positive values. So the CableTrench problem is actually a hybrid of the minimum spanning and shortest path tree problems. So it's also important to note that it is NP hard, which means that for large problems, you can't guarantee optimals, you can only guarantee good solutions, and we do that through the use of efficient heuristics. So we're going to be looking at a couple different algorithms. We're going to briefly talk about Prim's algorithm, which is used in the minimum spanning tree case, Dijkstra's algorithm, which is used in the shortest path tree case, and then modified Prim's algorithm, or ModPrim, which is a hybrid of Prim's and Dijkstra's algorithms and is used very frequently with the CableTrench problem. So for Prim's algorithm, when we apply it to the graph that we had earlier, we get something that looks like this, and it has a total weight of 42, which would then need to be multiplied by tau to get the cost of this graph. But you can see here that we chose our edges in such a way that we picked the smallest overall edges to connect everything back so that we minimized our trenches. And then on the other hand, for Dijkstra's algorithm, our graph would look like this with a total weight of 108, which needs to be multiplied by gamma to get the total cost. And here, rather than minimizing our edges, we minimized our cables. And so you can see that the two graphs look pretty different from one another. But now if we're going to look at ModPrim, that's actually a hybrid of Prim's and Dijkstra's algorithm, as I said earlier, and it actually takes their cost functions and combines them into one cost function so we can minimize everything all at once. And when we apply that to the CableTrench problem and apply it to a graph, we get a solution that is a hybrid looking solution of the two algorithms. Sometimes it might look more like a minimum spanning tree or more like a shortest path tree, but that all depends on what our tau and gamma parameters are. And the way that this algorithm actually works is we initialize our solution tree T to just include the root vertex. Then we're going to look at every edge that has one vertex in T and one vertex out of T. And then you apply this cost function Dij there, where you just take the edge weight for each edge and multiply it by gamma, then add it to the edge weight multiplied by tau. And then you're just going to choose the edge that has the smallest cost function and add that edge and its associated vertex into your solution. And then you repeat it until every vertex is in. So we're going to actually walk through that a couple times, or a step or two, with the connected graph that we've been using. So here we have a tau and a gamma both equal to 1. So we can't just use minimum spanning or the shortest path tree solutions, because neither one of those values is 0. So we start with root 1 or vertex 1 in the solution as our root, and we're going to be able to look at edges 1 to 2, 1 to 4, and 1 to 3. So for edge 1 to 2, our cost function would be 7 times 1 plus 7 times 1, which is 14. For 1 to 4, it's 8 times 1 plus 8 times 1, which is 16. And for 1 to 3, it's 10 times 1 plus 10 times 1, which is 20. So 14 is the smallest of those three numbers. So we're going to pick edge 1 to 2 and put in that edge and vertex 2. So now our solution looks like this. And then we're just going to do that again and again until you have every vertex in the solution. And once we do that, we have a solution looking like this, which has a total weight of 161. And that actually is also our total cost, since we multiplied by tau and gamma along the way. And you can see that it has some resemblance to both the minimum spanning and shortest path trees, but it is not the exact same as either one of them, which makes sense since it's a hybrid algorithm. And then you can also use ModPrim on some variants of the CableTrench problem. Specifically, we're going to be looking at the Generalized CableTrench Problem. And the only real difference between the Generalized CableTrench Problem and the regular CableTrench Problem is that now we have two weights associated with each edge, because we have a separate weight for cables and a separate weight for trenches, rather than one overall weight. And so when we apply ModPrim to that, it works the exact same way, except now our cost function has WCEIJ times gamma, which is our weight cost times our weight, or our cable cost times our cable weight, plus our trench cost times our trench weight. And so when we look at the same graph from earlier, now our blue numbers are our cable weights, and our purplish numbers are our trench weights. And we still have tau and gamma equaling 1. So when we look at our cost function for edge 1 to 2, it would be 7 times 1 plus 13 times 1, which is 20. For 1 to 4, it's 8 times 1 plus 15 times 1, which is 23. And then for 1 to 3, it is 10 times 1 plus 18 times 1, which is 28. So 20 is the smallest of those three numbers. So we're still going to pick edge 1 to 2 and put in that edge and vertex 2 into our solution. And then when we do that again and again and get all of the other vertices into the solution, it winds up looking like this, which is still has some resemblance to Prim's and Dijkstra's algorithms, but it's still different, and it's even different from the regular CableTrench problem because of the additional edge weights given by the generalized CableTrench problem. And now everything that we've done up to this point has all actually been done by hand, but it can still take some time, and it was still a little bit time consuming. And for large graphs, it's not even possible to do them by hand most of the time. So we have to have some sort of a computer program to be able to look at large graphs or to be able to look at any graph fast. So to do that, my advisor, Dr. Lenquist, and I were able to write some code to perform ModPrim on random graphs for us, and he actually also was able to write a random graph generator. So I was able to generate 100 random graphs of varying sizes and densities, and then we applied ModPrim to each of those graphs 9 times for varying values of tau, and we kept gamma as a constant equal to 1. And so here's a little snapshot of what some of our results looked like. This is only 10 of the 100 random graphs, but you can see that we have our 9 different values of tau, and then each of our costs that was generated by our code. And so then based off of this, I would like to, from here, calculate optimal values for the random graphs using pulp, which we're working on currently. And then I want to be able to compare our ModPrim values for every random graph to our optimal values from pulp, just to see how ModPrim actually works and how good it really is, and then potentially look at ways we could improve ModPrim. So I would like to thank you for your time.